Now that we've got these equations relating the voltage drops in the semiconductor and the oxide to the metal semiconductor work function difference, let's massage these equations a little bit and get an expression that we can use for this V oxide, because as of now it's unknown. So we're going to get at this through the capacitance in the oxide. So we're going to remember that the oxide has a thickness T and it has a dielectric constant of its own. So the capacitance, geometric capacitance associated with this is going to be E naught, E oxide, the area, the cross-sectional area of the device, and then the thickness of the oxide. So now we've supposed that we've applied enough voltage that the band bending in the semiconductor has disappeared. So the bands are flat in the semiconductor, no curvature, meaning no depletion or accumulation of carriers. But you'll notice that there's still a voltage drop across the oxide. Okay, now we're going to introduce a new quantity, the gate voltage. This is the one that matters. So the gate voltage is going to be the voltage applied between the metal and all the way far away from the interface. So we have the surface potential in the semiconductor and the oxide voltage, which appear over here. And in order to reach flat band, what it means is that we have to apply a gate voltage which is equal to this quantity. Now, we can also write the general case. So if we have an applied gate voltage across the entire device, we can break that up into the portions that are distributed amongst the oxide and the semiconductor. So we're going to have a delta V ox and a delta phi surface. We're going to define these as the Vox for any voltage. So then if we if we use this equation, that the metal semiconductor work function difference can be substituted in for these two quantities, we can gather those together and say that this is the Vox plus the semiconductor, the amount of voltage dropped in the semiconductor, and then plus the phi ms for this case of a p substrate here that we considered to get this equation. So this is how this tells us how the gate oxide is distributed between these two things. Now the last piece is to look at how big this oxide voltage is. Now, for any applied voltage that differs from the flat band voltage, we're going to start accumulating some charge at this interface. So that charge can either be due to electrons or due to holes, depending on which way the voltage is. There's always going to be some charge that piles up against the oxide at the metals, in the metal. And just by this drawing, you can kind of see that these charges distributed on either side of an insulator can be represented very nicely by a parallel plate capacitor. And we have that the charge has got to be equal to CV. So if this is plus Q here, we know that this is going to be minus Q here. And we can then substitute in that this is really the voltage just that's dropped over the oxide, and this is the oxide capacitance. And then if we define this as our surface charge in the semiconductor, then finally we can make the substitution back in for V aux, and we get V gate is equal to minus Q semiconductor surface over the capacitance of the oxide, which is just this formula here, plus the amount of voltage dropped across the semiconductor. And then lastly, we have this work function difference, which is determined by the doping and the semiconductor doping, and the metal work function. Now at flat band, this term will be 0. So up here, of course, the difference between EI far away and at the surface is 0. And we could simplify this equation for our flat band gate voltage. Now I'll mention one other thing quickly here. We've talked about the surface charge density that's caused by the pileup of either electrons or holes as we start moving the voltages around and changing the band bending. But there could also be fixed charges associated with that metal semiconductor interface. And those would modify this flat band condition by adding another term in this equation. And we'll look at that briefly in a moment. So if we have fixed charge, we just have to add a term that looks very much like this into the equation. So our gate voltage is going to have an extra term, negative QSS. So this is the charge in the channel due to mobile carriers, electrons and holes in the conduction valence band. Then we're going to have a Q fixed. Now these have to do with interface states or perhaps impurities formed right at that interface between the semiconductor and the insulator. And again, your flat band voltage will be where this is 0. And then you can see that the flat band voltage is going to be at a gate voltage, which is changed by the presence of this fixed charge compared to the case without it. So there's one more type of charge density that we have to consider as we move through the 4 regimes of behavior of the MOS capacitor structure. So the last one is the charge associated with a depletion width in the semiconductor. So there's going to be a charge density here, which is given by E times the number of acceptors in a p-type substrate times x, the depletion width, the xd. And this is going to equal our qsd. Now we can also have this accumulation of charge here, qss, and then of course on the other side we have the appropriate amount of charge in the metal to balance out this parallel plate capacitor. So with the application of voltage, this term is going to change, this term is going to change, this term is going to stay the same, this term is going to change. So now we can determine the various important voltages. So the gate bias that gives you flat bands, this is found when phi s is 0. The gate bias that gives you the threshold behavior changing into inversion, which we'll show in the band diagram in a moment, this occurs when phi s is 2 phi f p naught. And again, I'm assuming a p-type wafer right now. So overall, this master equation is used. You may or may not have the the fixed oxide due to traps at the interface. And you can see that both the threshold voltage and the flat band voltage are going to change by the presence of that fixed bias. The other thing that's going to happen is we have to look at the relationship between inversion charge and this depletion width charge. So if we look here at a plot of voltage, and if we want to bring in a p-type material, if we want to bring it to inversion, it means we want the bands to curve downwards towards the interface, and we'll pile up electrons at that point. Now, if the bands are bending that way, it means that we've expanded the depletion width out in our any other type of junction, Schottky, PN, and this one. Now, the interesting thing that happens is this means we're going into reverse bias. At zero applied voltage, we've got some depletion width. But what happens is that depletion width saturates as a function of reverse bias instead of continuing to move as the square root of applied voltage. And the reason is that as you start piling up those electrons satisfy the charge neutrality with the electrons in the metal instead of having to have that charge balanced by the depletion width. And as we saw, this QSS is exponential it's proportional to the exponential of the surface voltage, whereas this here is only square root on surface voltage, and so the exponential quickly dominates. Now going into forward bias, we'll hit a point where the depletion width goes to 0, and this defines our V flat band. This is our V equals 0. And at some point over here, we'll hit threshold. And again, this is for a P substrate. And depending on which metal you've used, and if there's fixed charge, this curve might translate to the left or right. So it is actually possible to have the flat band voltage and the threshold voltage both in the negative applied gate voltage regime if there's enough other charges and work function differences. And similarly, you could shift them all the way to the other side. So there's no universal behavior in terms of the sign of the gate voltage which causes these phenomena to happen because of all these different types of charges you can have. We can just say that they're ordered with respect to each other. Flat band will always be more positive than threshold, for example, for a p-type substrate. So the last thing we need to do is just express what this XD max is, where it saturates at a constant value. So the XD is given by 2 epsilon naught epsilon semiconductor phi s over Q times NA, oops, and the whole thing square rooted. So at threshold, we say that we've hit our maximum XD. We then get a 4 here, epsilon naught, epsilon s, phi fp, and we're just substituting in that phi s equals 2 phi fp, q, and a. So this translates into a maximum amount of space charge density just by multiplying by q and na here. And then we can plug this in here, and plug this into this term here, and we'll get an equation for the threshold voltage. So I can write that here. So V gate equals V threshold. And this occurs where we substitute in this equation here. And we will have negative Q SS plus Q fixed all over C aux, and then plus this QSD max, which I can quickly substitute in for as E and A XD max, again all over C aux, and then plus phi S equals 2 phi FP, and then plus phi MS. So this is how we can solve for the threshold voltage at which we go into the inversion regime of behavior.